Hello everyone, welcome to our AutoPIPE Special Interest Group session, our SIG for June 2018. Our topic for June is AutoPIPE Interoperability with STAAD.Pro using the SQLite PipeLink format. So let's jump into our topic. Today's focus is going to be about, of course, our AutoPIPE Connect edition and how to, first of all, the step-by-step process for Pipestress and structural analysis collaboration in AutoPIPE, benefits for both structural and Pipestress engineers in adopting this PipeLink workflow, and we'll look at some PipeLink user case studies. One thing I'd like to mention before jumping into the AutoPIPE SIG is that my colleague and I, Kareem Rashad, who is the STAAD application engineer, we have decided to take the month of June with our special interest group sessions and to combine the topics. So this is a PipeLink integration session, which means that we're looking at AutoPIPE and STAAD with PipeLink. And so I will be talking about more of the AutoPIPE side. We will look at a little bit about what's done on the STAAD side, but I'll mainly be talking more about the AutoPIPE side, of course. And what Kareem is going to be doing next week in his STAAD special interest group session is going to be looking at the same interoperability workflow, but more from the structural engineering side or the STAAD side. So this shows my welcome email to Kareem's session. I will be joining, and I do recommend that anyone that is interested in this workflow and interoperability also joins that session. First of all, if you only do Pipestress, it's still good to join and to really understand what both sides would work on and would do in the full workflow. It's a great idea to do that. And second of all, if you do Pipestress and structural, which in some cases it is only one engineer doing both, of course you would need to learn both sides in detail. Additionally, if you do only do Pipestress and you work with structural engineers, either within your company or another company, maybe you can also forward this to them and mention that you'd like them to join because we would like to start using this workflow. Okay, we'll jump into our first subtopic here. We're going to look at the step-by-step process for Pipestress and structural analysis collaboration from the AutoPIPE side. So just quickly, an overview of what the steps actually are. First, the Pipestress engineer would run the Pipestress analysis in AutoPIPE. And of course, you want to make sure that Pipestress analysis is working, is satisfying the criteria and the requirements. Simultaneously, the structural engineer would run the initial structural analysis in STAAD.Pro. And similarly, he or she would want to make sure that the structural analysis is satisfying the structural requirements. At this point, a lot of engineering companies and a lot of engineers kind of stop and they say, okay, well, my piping analysis is good and his structural analysis is good, so we're good. On the structural side, a lot of companies go a little bit further and they take into account the piping loads, but they do that through hand marked up isometrics or printed out support load reports. And a lot of that has to be a manual entry on the structural side. So a lot of times the structural engineer takes this a step further and they will actually include the piping loads in their structural analysis, which is great. We want that because that's more realistic rather than just bulking up your steel or assuming some high standard loads. But it's painful. It's basically very painful to have to walk through that and have to manually mark up isometrics or print out different reports, get them over to the structural engineer physically. The structural engineer then has to actually import all of those loads and forces and moments into their structural model in STAAD. Again, manually, every single support, every single direction, and each load case. So it's a lot of work. On the Pipestress side, unfortunately, a lot of times we just stop here. Pipestress engineers just stop here. They run that initial Pipestress analysis and they say, okay, it's passing all of my requirements and criteria, so I think I'm good to go. That is not the best approach. The best approach is to take into your account your realistic model, which means that considering what your piping is going to be connected to, which a lot of time is a structural model. So we'll look into this a little bit further, but just want to mention that after those first two bullet points, a lot of times we stop, and that's not necessarily good enough. So the next thing we can do is we can export our SQLite PipeLink file from AutoPIPE, and we can import that SQLite PipeLink file into STAAD. And this export to import includes the piping geometry, and it includes the support load, so the support forces and moments for all of the load cases that are being considered on the piping side. Next, you want to transfer the piping loads to the structure, create some combined load combinations, and then rerun the structural analysis in STAAD. So this is usually the structural engineer that's going to be doing this. Not so much our focus today, but we will go through quickly the process of what is done. In this step, you're taking those loads from the piping and you're transferring it to the structure. You're creating some what we like to call superstructure combinations, which include both the structure and the piping. And then when you rerun your analysis in STAAD on your structure, you will, I guarantee, probably see some differences in your stresses that you're going to see in your structure. Of course, with that step, this also means that if you see some stress changes and now you're overstressed or you have a situation going on the structural side, then you have to actually do something about that. So you want to then the structural engineer would want to work their magic, make some changes, add some bracing, whatever they have to do to bring those stresses down. And again, to satisfy the criteria on the structural side. Once that is done, the structural engineer can then export the SQLite PipeLink file back from STAAD and then import back into AutoPIPE. And this time, in this direction of the workflow, this export to import includes the support connections. The support connections are going to be made on the STAAD side. So this time it includes the support connections, and we on the AutoPIPE side will automatically see those come in. On the AutoPIPE side, we would want to rerun our pipe stress analysis, and this time we're considering the flexibility of the structure that we're connecting to through our supports. And again, we may see some big differences. A lot of times it depends on your specific model, the flexibility of your model to start with, first of all, and also it depends on what type of load cases you're including. So dynamic load cases compared to static load cases, you will see a bigger difference. But this is a more realistic analysis considering that flexibility of the structure. And then lastly, this is not a one-time perfect done. If it is, that's great, but a lot of times it won't be. So you may have to iterate as required. So you may have to make some changes on the piping side. Of course, if you do make changes on the piping side, you want to run through this again. You want to check it again. If you changed your supports or your loads or your forces changed, you then want to run through this again because it's not the same. So you want to make sure that's okay back on the structural side again, and then back and forth until you're seeing both sides are working well and satisfying the criteria. So let's dig a little bit deeper into this process. So we will look at the AutoPIPE side in AutoPIPE in a moment, but we're just going to go through the workflow with some screenshots and some explanation here of both the AutoPIPE side and the STAAD side. So first we start in AutoPIPE, and we want to run our initial pipe stress analysis. We have our piping model, we have supports. You can see there's a bunch of supports in there. There's V-stops and guides mainly throughout, and we have some anchors. And this just shows that in this example, what we sent back and forth, we're including gravity, 2 temperature cases, a T1 and a T2 case, so 2 operating cases, and then 4 earthquake load cases, static earthquake load cases in this situation. So we're including the positive X direction earthquake, the negative X direction earthquake, the positive Z direction earthquake, and the negative Z direction earthquake, just as an example. And we do have some V-stops in here that you can see are acting as rest stops, which means that they do not have a support above the pipe. And in order to take that into account, or any gap on your supports in AutoPIPE, in order to take the gap into account, we have to run what's called a nonlinear analysis. So you can see on our analysis sets dialog box to the right that we are running, here we go, first of all, nonlinear analysis. And when we do that, hopefully as AutoPIPE users, you're all familiar with this topic. If you're not, please take a note down of the words nonlinear analysis and start to look into it so that you understand it. It's a very important topic in AutoPIPE when you're running Pipestress analysis. And if you do need some help, you can get in touch with me again for that. But we're running a nonlinear analysis because we want to take into account the gaps on our supports. And if we have friction, also the friction on our supports. And so we have 3 analysis sets set up here. One with gravity as our initial state for our occasional loads, or in this case, our earthquake loads. One with our OP1 case, operating 1 case, as our initial state for our occasional loads, our earthquake loads. And then the third one has OP2 as our initial state for our earthquake loads. So we run an analysis and just quickly review the results, and just focusing here on 2 results. We have our code stress plot on the left, the upper left, which is showing that our highest stress is occurring at point C11 in the expansion case. And if we looked into, and we'll look at this in AutoPIPE also, but if we look into the dialog box, which shows a little bit more detail about what's occurring at that point in the different load cases, we would see that the highest ratio is 0.68 at C11. So we're not overstressed by any means, but we get an idea of the stress results that we're getting. And that's our initial stress results when we're considering these supports as completely rigid supports. They are infinitely rigid supports. Basically, you're saying you're connecting to a slab of concrete at every support. As we go into our STAAD model next, we'll see that that's not the case. We're not connecting to concrete at all. So this is not exactly a very realistic model at this point, but it's a good estimation, especially for a first run through. On the right side, on the lower right side, what I'm showing here is I also ran a modal analysis, because what you're going to see change in your piping model when you connect your piping and structure is the flexibility of the model. And when we talk about flexibility of a model, we're basically talking about our modal analysis, our frequencies, our natural frequencies that we're going to be able to extract from that piping model. They depend on the flexibility of the piping model, or the rigidity of the piping model. So what we see to the right in our frequency report is that we have a natural frequency. My first frequency, mode number 1, is 4.522 hertz. And we're capturing 112 modes. It looks like 113, but I'll show you when we get in there. The 113 is actually not capturing additional participation, mass participation. The 112 modes is what we're actually using to extract the mass participation. And our cumulative average mass that we're seeing is 79.66% of modal mass. We're able to extract 79.66% of our modal mass, and this would be used for our dynamic analysis results if we added in a dynamic load. We will see how this changes. Simultaneously, the next step is that simultaneously we run an initial structural analysis in STAAD. So this is just showing some screenshots that Kareem has helped us out with, and he will be showing more detail of on his side next week. But this shows the structural model in STAAD on the top left. And then the bottom right there is just showing the same model, but in a rendered view. So we can see that we have beams that are our main supports, our main members that are going to be supporting our piping. And then to support that, we have some bracing throughout there. So what Kareem did is he ran an initial analysis on the STAAD side, and we have some results here. If you're not commonly working in STAAD, then this might not be immediately readable to you, but that's fine. We're just going to focus on a couple of things and look at how they change. So basically what we're reviewing in our results here is we're just focusing on one beam. We're focusing on beam 502 in the top right here. And we see that our stress at that beam is 4.365 KSI. Okay, so that's a number that's important to us. We're just going to be comparing that beam. At this point, what we're looking at in our results down here for our corner stress and maximum stresses is we're looking at these equations, 7, 8, and 9, which is basically just reviewing the structure combinations only including structure, and they're just some combinations that are including dead loads, live loads, and operating loads. It's kind of all we have to really understand on our side, and he'll definitely dig deeper. To the left, it just shows the combinations that he has set up in STAAD. And again, we were just specifically looking there at 7, 8, and 9. So you can see the earthquake load being considered in there, a dead load and a live load, your thermal case. Okay, again, we're going to use these results to compare after we actually add our piping. So the next step is to export our SQLite PipeLink file from AutoPIPE. If you're familiar with the PipeLink workflow from the past, from before the Connect edition, the workflow is similar. It's very close. It's pretty much the same. But we're using, instead of the PipeLink file or the .PipeLink extension, we're actually using a SQLite PipeLink file. So it's a little bit different. But basically, the first step is for the mechanical engineer to run the piping analysis as we did, and of course, make sure it satisfies the code and project requirements, and then export the piping model along with the locations and the support loads to STAAD.Pro so that the support loads can be incorporated into the structural model. Your piping system can be supported in AutoPIPE by any configuration of 10 different types of supports, including anchors, and they can represent actual component pipe supports like a pipe rack or a cradle or a shoe that will actually be connected to the structural components. To ensure that the design of the structure is capable of sustaining the loads that's imparted by the piping system, the AutoPIPE model with the support configuration and the analyzed support loads can be seamlessly transferred to STAAD.Pro and applied to the structural model. So what this just shows is a couple of screenshots. On the file ribbon, we go to export, the export pull down, and we can see model to STAAD using SQLite PipeLink. So it's going to create a .pipelink.db file. That brings us to the PipeLink export dialog box where we can add some revision comments, and we want to check on where it says export support loads. That will go through the export and give us some log messages about what it successfully or did not successfully, if it didn't, actually exported out. And that creates in our File Explorer a pipelink.db file. So using this command enables the user to export the piping support data along with its connection and loading using the SQLite PipeLink option here, which is an advanced structural model data exchange used to exchange model data with STAAD.Pro. And the data will be exported to a SQLite database file. PipeLink's going to automatically create this file for us, as we see in our model directory, and then it can be used to be imported into STAAD. So that's what we see here. Once the structural engineer, as we saw, ensures that the structural model the initial run-through is acceptable, he or she can then import the SQLite PipeLink file into STAAD. So on the piping module in STAAD, he can select import. So over here, there's an import option, and can select the file that needs to be imported, and it will run through importing the file data, and it will tell us that the import has been complete. Next, what happens is the structural engineer goes through and will be able to connect the pipe supports to the structure using some rules and criteria that he or she sets up in STAAD. So on the top left, we can see that we have all of our available supports there. that we can pick from, and we can choose what we actually want to select over here to be connected to the structure. So in this example to the right, we see that we've selected all of our guides and our V-stops to be connected, but not our anchors. We're going to assume our anchors are connecting to something else, maybe some equipment or they're real end of run anchors, and we're not going to connect them. You may have different instances. You may know of some V-stops that are connecting to, maybe they are on the ground and they really are connecting to a concrete slab, or maybe there's different situations. They're connecting back to a vessel because they're really close to a vessel. So you may have different situations. You may not want to move all of your V-stops over and all of your guides over. This is just kind of giving an example. You do want to make sure you know what your supports are actually connected to. The next option is to select what beams you want these supports to be connected to. And basically what he's including here on the right, he's including all of the beams that you see highlighted in red, which are all of the main members. And he's leaving out on the left these bracings. We don't want to connect our supports to those bracings, so he's not even giving it as an option to STAAD. And then lastly, you have some connectivity parameters that can be set up. The maximum distance between your pipe support and your structural supporting point. If you want these to be perpendicular or you want to allow non-perpendicular connections. If you want additional nodes inserted. We do like to insert additional nodes for the integration, because then when we bring it out to AutoPIPE, there will be an additional node where the piping will be connected. I'll kind of show you that once we get into AutoPIPE. So for that reason, it is useful to keep that checkbox on when we're sending it back and forth. And then we see that we have some connections made. So the dialog box will show us what support is connected to what STAAD supporting point. And you can review that here. And this is the rendered model. You can see the piping geometry in here. In the rendered view, it's not so easy to necessarily see the connections, but we'll see that in a second. But you can see the piping geometry. You can kind of look through it. You can see how it's lining up. There is no clash detection directly in STAAD, but if you start looking in there, you can kind of get an idea if something looks like it doesn't fit right in there. Maybe if you need to move something over or reroute piping, whatever you might need to do. And then looking at the main view, the main STAAD view, we can see the connections that are made. So on a support, you can see there are some little dots, basically broken lines that are going down from the support itself or over from the support itself to where they would be connected to on the structure. So at this point, you definitely want to review it, or the structural engineer definitely wants to review it. If he or she is unhappy with any of the connections or wants to make some changes, it is more than possible to do it. Basically, when you run through this initial dialog box, what's nice is that if you have 150 supports in your model, it will automatically make some connections, and it makes some really reasonable connections that make sense. But we know once we get into a plant type of model that we have limited room, and sometimes, unfortunately, your supports don't make the most sense. You have to work around something or whatever the situation is. So if you have a situation like that, you can come into here and you can actually change the connection. It doesn't have to be what is automatically decided as the most sense by STAAD. So you want to review them, make any changes that are necessary for sure before continuing with your combinations and analysis. So again, once you get through that dialog box on the bottom of the piping tab in STAAD, you will again be able to review these connections in here. So it will show if it's connected to ground or if it's connected to a node. You will be able to assign a distance along the beam and check on a lever arm. So if the lever arm effect is included, then all of your pipe support loads will have the corresponding additional moments added to the structure. If they're pinned, then you don't check this on, and then the moments would not be added to the structure. But commonly you would want these moments to be added to the structure. So in this example, as we can see on the right, he does check them on, and he will go further into this in his presentation, but I just want to mention that option. The next step is to transfer the piping loads to the structure. So there is a option, a button to transfer the piping loads, which will bring up this dialog box that we see here. And if we zoom into that dialog box, we can see basically what it does is it takes our piping loads and it imports them into STAAD, it brings them into STAAD, and it presents them as an option to the structural engineer to transfer them to the structure. So we have, remember, we had gravity, 2 temperature cases, and 4 earthquake cases, but we had 3 different analysis sets with them in it because we were running a nonlinear analysis. So you can see gravity in the first analysis set, second analysis set, and third analysis set, and so forth. So what he will do is he will decide to either create this case in STAAD or to perform no action for this case in STAAD. Basically, no action is just ignoring that load case. And he can bring it in as a reference load and then assign a STAAD load number, a STAAD reference load number to it. So that they will automatically be assigned, but they can be updated or changed as necessary. If you're bringing it in, you're creating that reference load. The structural engineer has to assign the type of load that it is. There will be some automatic default types of loads that are brought in, but commonly it will be changed on the STAAD side. Like how we see a certain load case isn't on the mechanical side isn't always exactly how they reference it on the STAAD side. So Kareem will also be going into that. I think one of the common things he does is he changes this temperature to like a live load or an operational load for seismic. So he goes through and he actually explains on the structural side the way the loads need to be applied correctly. Now this does require communication between the piping and the structural engineers, because the structural engineer, when he gets this, he's not going to necessarily know what they mean. It's nice it has a note so you can see the temperatures of the thermal cases. You can see the direction of the seismic loads. That's great. You can see it's static, so that's good also. But most structural engineers wouldn't automatically understand what the number in the brackets means. So when we see 1, 2, 3 on the piping side, we know that that's our analysis set number, but he doesn't necessarily know that. So we have to communicate whether we're sitting at the desk together and just making sure that they're aware, or a really good idea would be like an Excel file write-up or some type of a file write-up just to say, you know, this is what this load case is representing, and make sure they fully understand before they go combining combinations on their side. So that does take some collaboration, but that's not much. And then once you do it once, it's kind of set, even if you have to iterate back and forth. It's not something that's difficult to do. So this shows that he actually took those, he referenced them in their reference load, and now he created some combined load combinations. Again, Kareem will dig deeper into this, but basically we see some combinations here of seismic pipe and structure. Down here you could see the dead load structure and pipe with the live load. So we see the structure and pipe being included in a lot of these cases. So we're creating superstructure combinations, basically, where we're looking at not just the structure load, forces and moments and loads, but also the piping forces and moments that are going to be added to those connection points on the structure. So then once he creates those super combinations and they're all making sense, he fully understands what our load cases are, he can then decide to rerun the structural analysis. And in this example, we are just looking again at the same exact beam and the results. So again, we're looking at different combinations down here. And you probably did not memorize what those combinations look like down here, so that's not a big deal. But we are looking at different combinations because before we were just looking at the structure, dead load, live load, and operating cases, and now we're looking at the structure and piping, dead load, live load, and operating case. And what we see, looking at the same beam, 502, actually on the next slide I have them next to each other. So what we see is that we had at one point, when we were just looking at structure, a stress on beam 502 of 4.365 KSI, and now on that beam 502 again, with the piping and structure both being considered, we're looking at a stress of 6.52 KSI. Okay, so we see the increase, we see the change. On the structural side, I would say that the stresses would increase commonly, usually always. I would think always, but I'm not sure on the structural side, but I would think always. We'll see a little bit of a difference on the piping side in a moment because piping is a little bit different. We're not adding additional load, we're taking into account flexibility, so it's different. But on the structural side, we're adding load. We're always adding load to this. So you're going to probably see some increases in stresses. Is it too high? Well, not for me to take into account. I do think that this is, he had mentioned that these are a little bit overstressed. So I think he's going to work that out on his side in his session. So he probably would want to make some changes to his structural model because it is a little bit overstressed and he wants to bring those stresses down. So again, in whatever way possible, increasing the member size or adding bracing, whatever the structural engineer decides to do to make sure that, again, they're satisfying their criteria. But here it just shows the example of the increase in the stress. Once he goes through, he makes his changes, he does what he needs to do, and he brings down the stresses and satisfies his criteria. He can send out the SQLite PipeLink file from STAAD so that there's an interop option in STAAD, an export option, and then he will be sending out another pipelink.db file that I will then be able to receive from him. And on the AutoPIPE side, I can then insert the model from STAAD using the SQLite PipeLink file. I want to go find that exchange file that he has given me, and I'll load it into my PipeLink import dialog box. Once I do that, you can check the revision history. So I can see I had created this at whatever point I sent the file to him originally with the AutoPIPE loads to STAAD. And then I can decide, you have some options here. What we're focusing on here and what we recommend to do is to always import the structural model loads and pipe connections, including the imposed point dead loads and the support connections. And then once we do that, we will see that our import progress dialog box will start to be updated with what was brought into AutoPIPE, and in the end we'll see that it was complete. We have the option, once it's complete, to view a log. So this is going to be a log that tells us everything that was brought in, the sections that were created, the number of beams that were brought in, the number of anchors and dead loads, and also anything that's been updated. So those support connections are being brought in. We can review the support connections that are being brought in. Here on the right, we see a dialog box showing those. So we can see at support A51, it's a guide. It had been connected to ground, and it's now being connected to point 49 in our piping model, which is going to be a beam point. And you have the option if you want to accept these connections or not. If you want to say no, I'm gonna assign a different connection here, you can uncheck one of those options. You don't have to accept every single connection, but you would then have to make sure you communicate back with him also. And then once you accept those, you can then again review an import log. This is a log file that's going to be created for you in your model directory. And again, it just shows where each support is connected to now and where it was previously connected to, which all of ours were connected to ground previously. So what we see here is our model with the structure brought in. You can see that structure, and we can see the pipe supports are connected. So just taking this and zooming in a bit, we have a support, and we see in the support dialog box that it's now connected to point 60 rather than ground. And that's automatic. So I'll show you that in a moment. And again, this is just showing the same model. It's showing it in line view, single line view instead of solid model view. So just focusing in on this support, you can see that this is coming from the piping, the black line here, going down to this orange line, which is the beam, and it shows that it's connected to that point there. So on our side, we would want to rerun the pipe stress analysis in AutoPIPE. We want to make sure we consider the flexibility of the structure. That's the whole point of this interop on our side, on the AutoPIPE side. And we get some results. They are a little bit different. So let's just take a look at the comparison. I think that helps. So you can just see the plots right away. Actually, these are backwards, so I apologize for that. This was the first run, the initial run, and this is the second run. So after the structure, obviously, because it has structure in it, but just to mention. So you can see the color plot just looks a little bit different, nothing drastic. Remember, we're not including any dynamic loads, but even with just static loads, we are seeing a bit of a difference. So the highest stress was occurring at point C11 in the expansion case with a ratio of 0.68. And now, after the structure is imported and the support connections are made, it's occurring at point D5 in the expansion case with a ratio of 0.65. So actually, our ratio has gone down. It's not the same as STAAD or structural side where it's always going to increase. Ours has gone down. So actually, the flexibility in this case made our stress analysis more acceptable. Not always going to happen, so don't look forward to that. But it can happen, especially when you're just including static loads. With dynamic loads, you will see a bit more of a difference commonly. And the reason for that is because we have our modal analysis results comparison also. So your dynamic results depend on your modal results. So just showing you these modal results previously, which is the one to the left. So this is your first one. This is after we bring the structure in over here. Originally, our modal analysis shows us that the natural frequency is 4.522 hertz. And after the structure is brought in, it's 4.311 hertz. So not a drastic, crazy difference, but we are seeing a different natural frequency. It's changing a little bit. So we went from a more rigid model to a more flexible model. And originally, we were extracting 112 modes, so which was capturing 79.66% of our modal mass. And now that it's a little bit more flexible of a model, we are extracting 184 modes, so a whole lot more modes, running this up to 200 hertz cutoff frequency. And we're now extracting 84.36% of our modal mass. So we're getting about 5% more of modal mass. Anyone who's tried to run modal analysis and extract modal mass knows that that's actually a pretty large increase without changing your cutoff frequency. So that can make a big difference in your dynamic results. Okay, that's the general overview. One other thing I'd just like to mention here is that we can import multiple STAAD models into a single AutoPIPE model. So you have the option during the import process to remove any previously imported structures. If you do that, you'll only be importing one at a time. But if say your structural team broke your plant model up in a different way than the piping team, then you might have different structural engineers working on the structure that attaches to your single piping model. And in that case, you can import all those different models in so that you have a complete piping model, even though the structure was broken up differently. Let's talk about benefits, and then I will go into AutoPIPE and just quickly show you the workflow that we've talked about. So benefits for both structural and pipe stress engineers in adopting the PipeLink workflow. The integration between AutoPIPE and STAAD that we talk about a lot, that I've gone through today and that Kareem will be going through on the STAAD side next week, it's the only one of its kind. It's the only integration out there like this, and it's a single or multi-user modeling environment with full bidirectional exchange of data. So basically, it could be one engineer working on both sides. It can be a couple of engineers working on both sides. It's a bidirectional exchange. You can send models back and forth to each other. And you can import, again, multiple models from the opposite side. So This integration it's got a ton of benefits. It really does. It's going to lead to faster design. You're combining your structure and your piping model with your changed and updated piping loads automatically. And this can be updated multiple times in STAAD. If you have to go back and forth, not having to mark up stress isometrics is huge. As somebody who had to do it in the past, anyone else who has had to do that in the past knows that it can be a pain. Anyone who's had to read marked up stress isometrics in the past knows that it can be difficult to read other people's messy handwriting and to really understand what they're trying to get at when they're writing them up. So this is automatic, and the more times you have to iterate, the more beneficial this becomes. And to transfer the piping and support loads in this case, not only because it's frustrating and difficult to do, but it takes a lot less time when it's an automatic transfer. And it also ensures more accuracy, because when you're marking things up by hand, it's easier to make a mistake. In this case, we take into account the structural sway and stiffness. So we look at the combined structure and piping model to analyze the true combined stiffness instead of assuming rigid or assuming a certain stiffness value. And this allows us to have both more accurate and safer structural designs and piping designs. So we're not making any assumptions anymore. We are looking at, on the STAAD side, our accurate pipe support forces and moments. And on the AutoPIPE side, our realistic structural flexibility. That's huge. Rather than just assuming some standard high loads on the STAAD side and assuming a rigid structure on the AutoPIPE side, we're looking at what's actually going to happen. And all of this leads to cost savings, because you have the ability to also run what's called a clash detection with these models, and that helps you to avoid costly redesign and construction delays. And we have potential cost savings also on pipe supports and steel structure, because again, instead of assuming some standards, like some standard steel member sizes and some standard pipe support sizes to take into account high loads that you might not even see, you can now actually take into account the realistic loads and flexibility, and that might bring those sizes down a little bit. So some additional advantages: it's basically closing the collaboration gap between design teams, and the interoperable design applications bring powerful change to dispersed design teams using varied software applications. Using modern workflows with interoperability, companies can save countless resource hours and lower project costs. Project teams across all disciplines can be confident that all of the stakeholders have access to the most up-to-date information, because it's a file that can be shared either with a data collaboration server or a share file type of site, however, or a network, however your team does share this information. And it can be shared across the piping, structural, and CAD departments. And this ensures that their piping and structural designs will automatically adhere to the current standards and codes. And using these optimized workflows, your engineers can confidently produce precise and accurate designs to greatly reduce the risk of operational failures. We don't want to see these problems with really flexible structure out in the field. We want to catch it before we actually send these out. We send our final drafts out, right? We want to catch this in our analysis phase. I just have my piping model here. So what I'm going to show you is basically just the piping side. We did look at it. It's all from this model, but just to show you the actual workflow. So on my side, I have a static earthquake, 4 static earthquake cases, as I mentioned. Positive X, positive Z, negative Z. I have, let me show you my input grid. I have 2 operating cases, so 150 psi and 392 degrees Fahrenheit, and then 230 psi and 410 degrees Fahrenheit. And I have supports that have gaps. So I want to take them into account. And so to do that, I again need to run a nonlinear analysis. So I'm setting this up as a nonlinear analysis with the initial state for occasional loads to gravity OP1 and OP2 for the 3 different analysis sets. Again, if this is new to you, please look this up in the AutoPIPE help on the AutoPIPE wiki page. Please, please, please learn about nonlinear analysis. It's very important. And I can run my analysis. And I'm just running that static and modal in this example. So it runs through. I'm going to get a message about V-stop liftoff occurring. So the pipe is moving up off of the V-stop. It's just a warning message, and I'll accept that. It happens in all 3 analysis sets. And I can review the results. Just taking a look at my code stresses, I'm going to look at all of my combinations. So I have everything turned on right now. Of course, I'd want to go in here and make some sense of my combinations, but just to quickly run through. If I look at a review of all of my combinations, my ambient to T1 case is causing the highest stress at this point, C11. I'm sorry, I said C11. I think it was always C12N. I saw it wrong in the picture. And that's 0.68, a ratio of 0.68. So at this point, let's say my code stress is okay. I'm seeing that. Let's say that my support loads are okay. My displacement criteria is okay. I know there's more to check. My equipment loads are okay. So let's say you checked everything and everything's okay. I can export this out to STAAD using the SQLite PipeLink file. I can update this if I want with a comment. And I have export support loads checked on, and I can say, okay, it runs through, and it's going to tell me that it exported successfully. So then I can close this. That quickly pops up, which creates that SQLite database file for me. So I would then take the file that was created. Let me go into here and just show you. I'll show you the folder that I'm working in. And I can show you that the last thing modified, 154, was this AutoPIPE integration model.pipelink.db. This is the file that I would then want to send to Kareem or my structural engineer. He would do his magic on that side, a lot of the stuff that we went through and more that he'll talk about next week. And then what he would do is he would send me his pipelink.db file or SQLite PipeLink file, which is what I have here. He already sent it to me. So this is what I have here. So this is what I would then want to import into AutoPIPE. So I can then come up to File, Insert Model, Model from STAAD using SQLite PipeLink. I want to navigate to that file, AutoPIPE 2. It's going to load it in through that SQLite database file that is created. And then I want to walk through these steps. So I can check my revision history. I'm importing the structural model, the loads, and the pipe connections, including the imposed point dead loads and the support connections. It will import. It tells me it's complete. I can choose to view the log if I want to. This creates a log for me in my model directory. And I can say finish. It goes through what it's connected to now, what it was connected to. And I can choose to view an import log, which is similar. So I'll just say no. And zooming in, we can see that my supports are now connected. So this is the support. It was connected to ground. It's now connected to 0.60 in AutoPIPE. So what that does is it automatically, when we on the STAAD side say to insert a node, what it does is it actually inserts a node along the beam for AutoPIPE that will be connected to. So that's a useful option to check on. And then if I just rerun my analysis again, we will see those other results. Again, getting V-stop liftoff, it's just a warning message. My modal takes longer because, as we saw, we're extracting more mode shapes, so it's going to take a little bit longer than it did. And if I look at my code stresses, again, for all my combinations, I now see the second plot that we saw. The maximum is here, it's behind a beam, but it's occurring at D5F, the far point of a bend, and it's a 0.65 in the expansion case. So it went down in this case, but that will not always be the situation. A couple things I want to mention because I'm cutting it real close. In your IMP file export and insert model pull downs, you will still notice that there is a regular STAAD using PipeLink option. That's if the STAAD engineer, the structural engineer, is not using STAAD Connect. So we can still connect back to the older STAAD version. We recommend using AutoPIPE Connect and STAAD Connect for all the newest features and the latest benefits, and in that case you would use pipelink.db. But if they're using not connect edition of STAAD, you would just send them a regular PipeLink file. So you'll still see that option in there. I do have case studies. I'm going to post this on the Learn server along with the video. So if you want to review those case studies, it will be posted on the Learn server. And I do have some contact information here. On the Bentley website, you have the access to learning about the Connect Edition, our AutoPIPE product data, events, training, downloads, Bentley communities. Always take a look for our Bentley events. We have webinars and tech talks and SIGs and so much stuff that is available complimentary to our users coming up all of the time. So I would definitely recommend to go to our events page and our webinars page and to look into what's coming up next. Specifically, recommend joining next week's session with Kareem. It's going to kind of bring this into a full circle and show the other side of things.